Hello everyone, and welcome to our session on deep learning. I'm Dr. Aris. Today, we begin a journey into the technologies that power everything from voice assistants to autonomous vehicles. Before we look at the how, let's establish exactly what deep learning is within the landscape of modern computing. A common point of confusion is the relationship between artificial intelligence, machine learning, and deep learning. Think of them as nested layers. Artificial intelligence is the broad goal of making machines smart, while machine learning is the set of algorithms that allow machines to learn from data. Looking at this Euler diagram, you can see that deep learning is a specialized subset of machine learning. It specifically uses multi-layered neural networks to handle complex, high-dimensional data. The real breakthrough here is the paradigm shift in feature engineering. In traditional ML, humans had to manually identify which features of the data were important, like identifying the edges of a shape. In deep learning, the model automatically extracts these features through its hierarchical layers. This deep learning revolution didn't happen by accident. It was driven by two core factors: the explosion of big data, which provides the massive training sets these models need, and the development of high-performance GPUs, which allow us to perform the necessary billions of calculations in a reasonable time frame. This foundation sets the stage for our entire course. Throughout the next several modules, we'll dive deep into these neural structures. Maya, before we move on to the math behind the perceptron, what kind of real-world problem are you most excited to see these models tackle? That's a great vision for the future of AI, Maya. To realize those creative applications, we first need to master the internal logic of the neuron itself. Let's examine the fundamental unit, the perceptron. At its heart, the perceptron is a mathematical operation. As you can see in this formula, it calculates a weighted sum of all input signals, denoted by W and X, and adds a bias term, B. The weights represent the importance of each input, while the bias allows the model to shift the activation threshold. Think of it like a flexible dial that helps the neuron decide when to fire. This diagram illustrates the flow. Inputs are weighted, summed at the node, and then pass through an activation function to produce the final output. The activation function is key because it introduces nonlinearity. This table compares common functions like ReLU, sigmoid, and tan. Leo, you'll want to note the ranges and mathematical properties here, as they'll be critical when we analyze gradient flow in later chapters. Now that we've seen the anatomy of a single unit, let's see how well you've grasped these foundational concepts. Now that we've grasped the fundamental unit of the perceptron, let's zoom out and see how these units come together to form the complex architecture of deep networks. Our journey begins at the input layer. As we just discussed regarding data vectors, this layer is the entry point where raw signals, like pixel intensities from an image or numerical vectors from text, are first processed. Next, we move into the hidden layers. This is where the deep learning truly happens. By stacking these layers, the network is able to learn a hierarchy of features, moving from simple edges to complex object parts. If you look at the diagram here, you can see how information flows from the input through these intermediate stages before reaching its conclusion. That conclusion is reached at the output layer. Depending on our task, this layer will provide the final predictions, whether it's identifying a category in classification or a specific value in regression. We also have to consider the connectivity between these layers. While many models use dense layers where every neuron is connected to the next, we often use sparse connections to improve efficiency and focus on specific features. Just a final note for your technical vocabulary. When we refer to the depth of a network, we are simply counting the total number of these processing layers. With this structural foundation in place, let's see how we can optimize these connections. Now that we've seen how layers are structured, we need a mathematical way to find the optimal weights for those connections. On your screen is a 3D loss landscape, essentially a map where elevation represents the error of our network. Our goal is to navigate to the lowest point. Think of it like a hilly terrain. We want to get that ball to the very bottom of the valley, which represents the state where our model makes the fewest mistakes. This visual process is exactly how gradient descent works in a real training loop. To begin, look at the learning rate slider. This control determines how large a step we take down the hill during each iteration. Try setting it to a moderate value and click the Step button to see the ball begin its descent toward the minimum. Dr. Aris, as I click Step, I'm noticing the ball always moves in the direction where the slope is steepest. Is that because we are calculating the negative gradient of the loss function at every single point? Precisely, Leo. Now, let's see what happens when the learning rate is poorly tuned. Try sliding it to the maximum setting and clicking Step. You'll see the ball bounce wildly across the valley, or even fly out of the bounds. This is what we call divergence. Experiment with different rates to see how they affect the weight changes. Finding that Goldilocks setting, not too fast to overshoot, but not too slow to stall, is the core challenge of the optimization process we just began exploring. Now that we've seen how optimization goals are set, let's examine the engine that powers it. Backpropagation. Building on the gradient descent concepts we just covered on the previous page, this is the specific mechanism neural networks use to calculate exactly how much to adjust each weight. The process is a cycle consisting of two main phases. First, the forward pass, where data moves through the layers to calculate the current error. Second, the backward pass, where we use the chain rule to distribute that error back through the network, layer by layer. As Leo might appreciate, the mathematical heart of this is the partial derivative. We are calculating how the total loss, L, changes with respect to a single weight, W. This value is our gradient, the compass, that tells us which way to move to reduce the error. By following these gradients toward the local minimum of the error surface, the network slowly learns. However, keep in mind that in very deep networks, these gradients can sometimes vanish or explode, making training difficult, a topic we will revisit shortly. To help you visualize this abstract flow, let's watch a short demonstration of how data and gradients interact during a single training step. Now that we've explored the mechanics of optimization and training, let's apply those principles to the most iconic architecture in deep learning: convolutional neural networks, or CNNs. This is where AI truly began to see. The breakthrough here is the convolution operation. Instead of every neuron being connected to every pixel, we use sliding kernels. These kernels act as filters that extract spatial features, allowing the network to understand local patterns regardless of where they appear in the frame. Maya, I know you appreciate the visual side of these networks. Let's watch this short clip to see exactly how these kernels transform an image into a structured feature map. What's truly fascinating is this filter hierarchy. The first layers only see simple edges, but as we stack these layers, the network begins to recognize shapes, and eventually, complex objects like faces or cars. It mimics the human visual cortex. We've come a long way from the original LeNet 5. The evolution to architectures like ResNet allowed us to train hundreds of layers deep by solving the gradient issues we discussed on page 6. Next, we will see how these spatial concepts adapt when the data has a temporal dimension. Moving from the spatial features of images we just covered in the CNN module, we now shift our focus to data that has a temporal dimension: sequences. In traditional networks, inputs are independent. But for text or time series, the order matters. Recurrent neural networks, or RNNs, solve this by using a loop mechanism where the hidden state at one time step is passed as an input to the next, creating a form of internal memory. However, as the sequence grows longer, standard RNNs suffer from the vanishing gradient problem we discussed on page 6. They effectively develop short-term memory, forgetting earlier information in a long sentence or data stream. To fix this, we use LSTMs and GRUs. These gated architectures use forget, input, and output gates to mathematically control the flow of information, deciding exactly what to remember and what to discard over many time steps. This gating mechanism is why your phone can predict the next word in a text, or how models can translate entire paragraphs. Whether it's neural machine translation or sentiment analysis, these architectures handle the context that feed-forward networks simply cannot. Building on the sequence modeling we just discussed with RNNs and LSTMs, we now reach a pivotal moment in AI history: the Transformer Revolution. This architecture shifted the paradigm from processing words one by one to processing them all at once. The core innovation here is self-attention. As Sarah often highlights in implementation, this allows the model to weigh the relative importance of every input simultaneously. It doesn't matter how far apart two words are. The model can attend to their relationship directly. Mathematically, this is defined by the scaled dot product attention formula you see here. Leo, notice how we use query, key, and value matrices to calculate these weights. This specific structure is what enables the massive parallelization required for modern LLMs like GPT. Maya, you'll love this visualization. It shows how the model sees word-to-word relevance. By looking at the thickness of the lines, we can actually see the neural network focusing on the relationship between a pronoun and its referent nouns. This is the very foundation of how machines now understand context. This transition from sequential to parallel processing is exactly what allowed us to start training on the entire internet's worth of data. Before we move into our next knowledge check, let's think about the efficiency trade-offs here. Now that we've solidified our understanding of advanced architectures on page 11, it's time to put that theory into practice. For our expert project, we are designing a deep learning pipeline to detect pneumonia from medical X-ray imagery. You'll be responsible for making the critical calls we've discussed today, deciding between CNNs and transformers, selecting loss functions, and implementing regularization to prevent overfitting on a small dataset. I will be here to guide the architectural foundations, while Sarah can help with the practical implementation hurdles. Leo is already looking into the mathematical optimization, and Maya is focused on the real-world impact of the solution. Please select a role that interests you, and let's begin the design process. We have reached the end of our intensive session today. We've journeyed from the very first principles of neural networks to the complex architectures that define modern AI. Let's take a moment to reflect on this path to mastery. Think back to where we started with the simple perceptron. Since then, we've covered backpropagation, optimization techniques like gradient descent, and the powerful transformer models we discussed just a short while ago. This evolution represents the backbone of the entire field. Looking ahead, your roadmap should include mastering MLOps and experiment tracking. The field moves fast, so making it a habit to read the latest research on ArcSiv and engaging with the open source community will be your greatest assets for staying current. As this symbolic integral suggests, mastery is the accumulation of mathematical rigor and practical application over time. Never stop balancing the why of the equations with the how of the code. It has been a pleasure guiding you through these deep learning foundations today. Great job on the design projects and the technical discussions. Keep building, keep questioning, and I look forward to seeing where your DL journey takes you next. Before we finish,